In last class, we discussed on basic concepts of thermal radiation. In this class, we are continuing with the same. Thermal radiation is defined as the transfer of energy across a system boundary by means of an electromagnetic mechanism which is caused by a temperature difference. Thermal radiation is a mode of heat transfer, just like conduction and convection. But the difference between conduction, convection and thermal radiation is, in conduction and convection, for the transfer of heat from one point to the another point, there is a need of system. That means there is a need of medium. In conduction, the transfer of heat from one point to the another point takes place due to the physical contact of the molecules. In convection, the transfer of heat takes place due to the movement of the molecules from one point to the another point. But in radiation, there is no need of any medium. This type of heat transfer even takes place in the vacuum. The best example is the transfer of heat from sun to the earth. Between sun and earth, there is no medium above the atmosphere. There is no substance, but the transfer of heat takes place between the sun and earth in the form of electromagnetic waves, and this mode of heat transfer is called the thermal radiation. Thermal radiation is a mode of heat transfer, is that defined as the transfer of energy which takes place across a system boundary by means of an electromagnetic mechanism, and this transfer of heat takes place only by this temperature difference. There is no need of any medium. The transfer of heat takes place solely by a temperature difference. Any solid or the liquids above the absolute temperature emits energy in the form of electromagnetic waves called thermal radiation. We know that the electromagnetic waves, when the bodies emits radiation in the form of electromagnetic waves, these electromagnetic waves travel at the speed of light, and the wavelength of this electromagnetic radiation continuously varies, and the difference between the radiation between different forms of radiation is made by only depending on the wavelength and frequency of radiation. The thermal radiation emitted by all the bodies lies between 0.1 to 100 micrometer wavelength. This is the wavelength that exists. The thermal radiation emitted by any body lies between 0.1 to 100 micrometer wavelength. The visible light or the sunlight emitted by the sun, the radiation emitted by the sun lies between 0.4 to 0.7 micrometer, and the thermal radiation also lies between 0.1 to 100 micrometer. Next, in last class, we discussed on the total emissive power. Total emissive. The next concept that we discussed in the last class is total emissive power. Total emissive power is defined as the total amount of radiation emitted by a body per unit area and per unit time. That is it is the amount of radiation which is emitted by a body per unit area for every unit square meter area and per unit time, and it's expressed in watt per meter square. Total emissive power is the amount of radiation emitted by a body per unit area of the body and per unit time. It is expressed in watt per meter square. According to Stephen Boltzmann law, the total emissive power of a body, of a black body, is directly proportional to fourth power of its absolute temperature. That it means the radiation emitted by a body is directly proportional to its fourth power of absolute temperature. The amount of radiation emitted by a body per unit area is directly proportional to fourth power of absolute temperature for a black body, where E suffix b gives the radiation emitted by a black body equals sigma into A into T to the power of 4. Here sigma is called proportionality constant, called Stephen Boltzmann constant, and its value is equal to 5.67 into 10 to the power of minus 8 watt per meter square to the Kelvin to the power of 4. The next concept that we discussed is monochromatic emissive power or spectral emissive power. We know that at a given temperature, the amount of radiation emitted by a body is not of the same wavelength. The wavelength of thermal radiation varies continuously. Therefore, monochromatic emissive power is defined as the rate of energy radiated per unit area of the surface per unit. Means it is the amount of radiation emitted by a body at a given temperature per unit area and at a particular wavelength, and it is denoted by the letter E suffix gamma, where gamma indicates the wavelength, and the total emissive power in such a case is given by integral of E suffix sigma with respect to gamma. E equals, where E is the emissive power, the total emissive power is given by integral of E suffix lambda with respect to lambda, where the integration is between 0 to infinity. That means the wavelength varies from 0 to infinity. The next concept that we discussed in the last class is emissivity. Epsilon. Emissivity, we know that the amount of radiation emitted by a black body is always higher than the amount of radiation emitted by other bodies, and the emissivity is defined as ability of a surface of the body to radiate heat. It is also defined as the ratio of total emissive power of any body to the emissive power of black body of equal temperature. Means when a black body and any other body, they are at the same temperature, the ratio of their emissive power is called emissivity. Emissivity is defined as the ratio of emissive power of any body to the emissive power of black body, which are at equal temperatures. For a black body, the emissivity value is always equal to 1, and for other bodies it is in between 0 to 1, and for white body, which rejects all the radiations, which doesn't absorb or any radiations, or which doesn't releases any radiations, epsilon value is 0 because it doesn't emit any radiations, and for real surfaces it lies between 0 and 1. Irradiation. Irradiation is defined as the total incident radiation on a surface from all the directions per unit time and per unit area of the surface. That means when a body is placed on a surface, on any surface, it receives radiation in all the directions, not in one direction. And irradiation is defined as the total amount of radiation that the body receives, that falls on a body in all the directions per unit time and per unit area of the surface is called irradiation. It is also expressed as watt per meter square. Its unit is watt per meter square and denoted by the letter G. When some radiation falls on a body, some of the radiation is reflected back, some of the radiation transmits through the body, and some of the radiation is absorbed by the body. The ratio of radiation absorbed by the body to the radiation incident on the body is called absorptivity. The ratio of radiation reflected by the body to the amount of radiation falls on the body is called reflectivity, denoted by the letter G suffix R. Similarly, the amount of radiation which transmits through the body to the total amount of radiation falls on the body is called transmittivity. Absorptivity, reflectivity and transmittivity. The ratio of radiation absorbed to the total amount of radiation falls on the body is called absorptivity. The ratio of amount of radiation reflected by the body to the amount of radiation falls on the body is called reflectivity, and then transmittivity. Absorptivity, reflectivity and transmittivity. Absorptivity is indicated by the letter alpha, reflectivity is indicated by the letter rho, and transmittivity is indicated by the letter tau. A black body. A black body is one which absorbs all the radiations which falls on it. A black body is one which neither reflects nor transmits any part of the incident radiation but absorbs all of it. In practice, a black body doesn't exist. Actually, it is an theoretical body. There is no surface which absorbs all the radiations. But for practical purposes, we assume a black body which absorbs all the radiation. For a black body, absorptivity alpha equals 1, transmittivity tau is 0, and reflectivity is also 0. Similarly, next is opaque body. A opaque body is one which doesn't transmits any radiation through it. Therefore, the tau transmittivity is equals to 0 for an opaque body, and alpha transmittivity plus absorptivity rho, absorptivity alpha and reflectivity rho, sum of these two becomes equal to 1 for an opaque body. It absorbs radiation and it reflects radiation. A opaque body absorbs radiation and reflects radiation, but it doesn't transmit any radiation. A white body is one which reflects all the radiations which falls on it. Therefore, for a white body, rho equals 1. It doesn't transmit any radiation, it doesn't absorb any radiation. Transmittivity is 0, absorptivity is also 0 for a white body. Next one is grey body. If the radioactive properties rho, tau, alpha of a body are assumed to be uniform over the entire wavelength spectrum, then such a body is called grey body. We already discussed that at any given temperature the amount of radiation emitted by a body continuously varies. Its wavelength, the wavelength of radiation continuously varies even when the substance is at a given temperature or at a standard temperature. A grey body is one in which its properties, thermal radioactive properties doesn't varies. Means its absorptivity property, reflectivity property or absorptivity property doesn't varies even if the radiation, the wavelength of the radiation falling on the body varies. For all the wavelengths, its property remains same. Such type of body is called a grey body. Therefore, a grey body is defined as one whose absorptivity of a surface doesn't vary with the temperature and wavelength of incident radiation. The temperature may vary or wavelength of radiation may vary, but its property doesn't vary. Its thermal properties remains the same. Its absorptivity remains the same. Its reflectivity remains the same. Its transmittivity remains the same. Such a body is called a grey body. Next is Planck's law. We know that at any given temperature the amount of radiation emitted by a body depends on wavelength of radiation. As the wavelength of radiation varies, wavelength of electromagnetic waves varies, the amount of radiation emitted by the body also varies. And Planck's law gives the relation between the emissive power of a body and wavelength. This is the relation between spectral emissive power of a black body and wavelength. The relation between wavelength and the emissive power is given by C1 into lambda to the power of -5 divided by exponential to the power of C2 by lambda multiplied by capital T minus 1, where C1 and C2 are the constant terms and lambda gives the wavelength of radiation. And Planck's law gives the relation between spectral emissive power of a black body and wavelength. By using this relation, we can find the amount of radiation emitted by a body at a particular wavelength and at a particular temperature. Next is Wein's displacement law. And the Wein's displacement law is stated as the product of absolute temperature and the wavelength at which emissive power of a black body is maximum is constant. That means we already know that, we already discussed that at a particular temperature the amount of radiation emitted by a body varies with wavelength. That means it varies from minimum to maximum as the wavelength of the radiation emitted by a body varies. And the product of wavelength at which the emissive power is maximum at a particular temperature, the product of this maximum, the wavelength at which emissive power is maximum and the temperature is always a constant. Whatever may be the temperature, It may be 20 degree, it may be 20 Kelvin, it may be 290 Kelvin, it may be 300 Kelvin. Whatever it may be the temperature, the product of wavelength at which the radiation emitted by a body is maximum and the temperature, the product of wavelength and the temperature is always a constant, and it is equal to 2898 micrometer. The product of wavelength at which the emissive power is maximum at a particular temperature and the absolute temperature is always constant. The product of these two values is always constant. This is what Wien's displacement law states. Lambert's cosine law states that total emissive power E suffix theta from a radiating plane surface in any direction is directly proportional to the cosine of the angle of emission. Lambert's cosine law gives the relation between the amount of radiation emitted, or the emissive power, it is the amount of radiation emitted in the direction normal to the surface, and the amount of radiation emitted by the body at any angle theta. Lambert's cosine law gives the relation between the amount of radiation emitted in the direction normal to the surface and in the direction at an angle theta to the normal. Normal is nothing but in the straight line, in the upward direction. The E suffix n gives the amount of radiation emitted by the body in the direction normal to the surface, and E cos theta gives the amount of gives the amount of radiation emitted by the body at an angle theta, E suffix theta. And the relation between this E suffix n and E suffix theta is given by the relation E suffix n equals E into cos theta, where theta is the angle at which the radiation is emitted by the body to the normal. The angle theta is the angle subtended by the normal to the radiating surface and the direction vector of emission of the receiving surface. If En is the total emissive power of the radiating surface in the direction of its normal, that means the Lambert's cosine law gives the relation between the radiation emitted by the body in the direction normal to the surface and the amount of radiation emitted by the body at an angle theta to the normal. Next is solid angle. In two-dimensional objects, to define the angle subtended by an arc, we make use of arc angle, or the angle subtended by an circumference. The circumference is given by 2 pi r, where 2 pi is the angle subtended by the circumference, which is equal to 360 degree. 2 pi into r gives the length of circumference, where 2 pi is 360 degree, the angle subtended by the circumference or the circle. Similarly, the angle subtended by a surface, by a small surface of a three-dimensional object, just like sphere. We can assume the earth as a sphere, or a tennis ball as a sphere, or a football as a sphere. And the angle subtended by a small surface of a sphere is called the solid angle, and is defined as the portion of space inside a sphere enclosed by a conical surface with the vertex of the cone at the center of the sphere. That means if you consider a small space on the surface of a sphere which can be enclosed by a cone such that the base of the cone is at the center of the sphere, then the angle subtended by that cone or the surface which is enclosed in a cone is called the solid angle. And this solid angle is given by the relation d omega equals dA by r square, where d omega is the solid angle, dA is the surface area enclosed by the base of the cone, and r is the distance between the base and the center of the sphere. dA is the surface area enclosed by the cone and r is the distance between the base of the cone and tip of the cone. A solid angle is defined as the portion of the space inside a sphere enclosed by a conical surface with the vertex of the cone at the center of the sphere, and it is given by the relation dA by r square. Intensity of radiation. Intensity of radiation is defined as the amount of energy leaving a surface which is emitting from a surface. Let us consider here it as dA1 is defined as the amount of energy which is leaving a surface in a given direction. In a given direction, let us assume here the radiation is passing, is emitting the surface, is leaving the surface at an angle theta to the normal, is defined as the amount of radiation emitted by a body in a given direction per unit solid angle and per unit area of the emitting surface normal to the mean direction in the space. That means it is the amount of radiation emitted by a body per unit area which is passing through a solid angle it is the amount of radiation leaving a surface in a given direction per unit solid angle per unit area of the emitting surface which is normal to the mean direction in the space. Here you will come to know the amount of radiation is the amount of radiation emitted. dQ1 to 2 gives the amount of radiation emitted by a body emitted by a surface dA1 per unit area. dA1 gives the area of the surface which is emitting radiation, dA1 into cos theta, because when you weave an object in the normal direction you will get an actual view, but when you weave an object from at an angle you will get a diminished object. Here we are weaving the object at an angle theta and it looks like dA1 into cos theta. That means the amount of radiation emitted by a body per unit area and passing through per unit solid angle. The solid angle is given by dA2 r square which is already defined.